lectures in the computer networks area, and I advise you to see his profile, see the software developed by him and his research group. And he has like one of the pioneers in computer network traffic modeling area. So especially when you study at master's level, you should be aware of, at undergrad level it's not nothing important. You should all need about the theory, not the guys who propose the theory. But in masters, you should look at the personalities as well. Just like I keep showcasing my personality, uh, but you also need to know about who are the authors who proposed methodologies, who are the personalities in your area, in your research area. So that's why, so Mark Rubella, I would advise that you can also take your assignments from his website, which we will talk about later. Um, so you can see that the two important points, which I'm not sure you can see the movement of my mouse here. There are two main uses for traffic modeling. Why do we do traffic modeling? I think in previous class I talked about challenges of traffic modeling, and I started about showing the superposition. Because in case of internet traffic modeling, the two main things which come into our mind is the analysis of the two physical phenomena. One is uh, superposition or multiplexing, which happens at router interfaces, and the other phenomena is traffic decomposition or demultiplexing, which also happens at router interfaces or switch interfaces. Uh, at switches, the level of multiplexing is quite high in terms of number of users. At routers, the multiplexing links, the number is less, but the traffic is more. So and we, if you remember in the last class, we talked about when we mix smooth traffic, two lines, we multiplex smooth traffic, what happens to the output traffic? If we multiplex one stream of random traffic with a smooth traffic, what happens? If we multiplex two streams of random traffic or busty traffic, okay, then what happens to the output traffic? Okay. And what if we do demultiplexing? Like if there is a certain link which has smooth traffic, and we demultiplex that traffic into three output links, so what will be the stochastic properties or statistical behavior of the demultiplex traffic? And what if we demultiplex the random traffic into two links? And so what should the underlying theory about this? So we finished last class by noting these challenges. We did not study any kind of mechanisms in underlying superposition and demultiplexing. We will study them later, and in these lectures you will know about these challenges more. So I think you all agree that when you talk of the uses for traffic modeling, I think in previous class we made it we I tried to make a table. uh, if you remember correctly, I tried to make a table uh, about the uses of internet traffic modeling, and I ask you all to help me in filling. I think you all helped me to fill, I think, around 8 to 9 points. And on the second column, I ask you about the limitations of internet traffic modeling. So I hope you still remember what you said in the previous class. What are the uses and misuses or limitations of internet traffic modeling? So here we are going a bit formal, and we are categorizing all of these uses, especially the left column, which I draw or wrote in the last class, that there are two main uses for internet traffic modeling. One is about performance analysis, and the other is about network engineering and management. I think that um, uh, can you tell me that our NOC guys are interested in, or our ISPs are interested in which factor, the performance factor or the network engineering and management factor?
The network engineering management factor.
And can you tell me about the uh, time scale? That is there any difference of analysis, that performance analysis and network engineering, do these two different tasks are related to time scales or not? I think I've give the answer is written in terms of hints that performance analysis is concerned with questions such as delay, throughput, and packet loss. Okay, and network engineering and management, uh, it is concerned with questions such as capacity planning, traffic engineering, anomaly detection. So these are things. So I think that these two tasks, although they seem related, but their the scale of implementation or the scale of analysis is somewhat very different. For example, if I start from performance analysis, then you can see that delay, throughput, and packet loss. So these kind of things, they appear, and they are monitored at the level of less than second, millisecond, microsecond. And in network engineering, at the level of our routers, we do not talk of nanosecond, we mostly talk of millisecond time interval, but these are sub-second analysis. When we talk of network engineering and management, then they are concerned with questions such as capacity planning, traffic engineering, and anomaly detection. So you can see that the capacity planning is an exercise. The time scale is about sometimes days, months, or even years. Same goes with traffic engineering and anomaly detection. Okay, so so I think you all know about capacity planning. What is the capacity planning? That how much should be the capacity of in terms of bits per second of outgoing link to offer better quality of service. And you all know about anomaly detection. I think in last lecture I talked a lot about my article about variable distribution and how others used it to demonstrate that variable distribution, a deviation from variable distribution, is an indicator of anomaly. I discussed a lot about this in previous class. Who can tell me about this, what we call as traffic engineering? What is traffic engineering? I think there are so many knock guys here. They can tell me better than what I can tell you. How can you define traffic engineering?
So we can explain it as a traffic pattern in peak hours and non-peak hours. As knock engineer,
Mhm.
we have to check the throughput in peak hours and non-peak hours. So there are difference between peak hours and non-peak hours traffic.
Mhm. So how will you, define? Will you have a different routing policies in peak hour or different routing policies in less peak hour? Do you mean by this?
Yes, sir. Some ISPs had done this. Suppose some ISPs give more bandwidth in non-peak hours, and in peak hours they give less bandwidth. They manage their traffic accordingly.
But how will you define mathematically? You are right in terms of telling the practices used by ISPs, but how will you define that terminology, traffic engineering? Because engineering is
Sir,
something. Yes.
sir, we can define by quality of service. We can prioritize our traffic,
Mm-hmm.
like we
Uh,
prioritize our VoIP traffic.
okay, that's something very near. And okay, let me give you a hint.
Sir,
Let me give you a hint.
okay.
I give you a hint that there is a terminology called as, I think all knock guys understand about this, the factor called as utilization. Utilization. Utilization.
There's a
Utilization.
utilization in peak hours. Utilization is more, and in non-peak hours the
गैर से
utilization is less.
कंट्रोल कर
So we
सकते हैं.
have to con-
Yes. So how, I want to understand what is the definition of traffic engineering, and how you ensure, and why do you do traffic engineering in the first place?
सर ताकि
Sir,
सिमेट्री ना हो, सोर्स टू डेस्टिनेशन एंड डेस्टिनेशन टू सोर्स, जो मेरा पैकेट जाना चाहिए वो सिमेट्री होके जाए.
Actually, we have students from Yemen and other, so we have to speak in English. Sorry for it.
That the symmetry
So,
of the packet should be maintained from source to
mm,
destination and destination to source.
mm. Any
sir,
other
I
comment
think,
on traffic engineering?
traffic engineering is done so that an ISP can monitor its bandwidth and
Mm,
limit its bandwidth according to the needs of its user. so that large chunks of data that are flowing through its wires and all, it should be managed. That's why they create policies such like as Fahad said, to
Mm,
accommodate large bandwidths in night times, and during day they accommodate low bandwidth
mm.
or something like that. Like I have
I
fiber link, I get 100 MBs in the day, and
mm,
it gets double in the night, 200 MBs in
mm,
the night. So
mm.
they define such policies.
Okay, so what my question is that you guys are talking more about traffic shaping policies. So these are traffic shaping policies. So although they are somewhat near to what I mean, but still I am not able to get the true meaning of traffic engineering. You can even consider in terms of civil engineering. For example, there's a road traffic. Okay, so think about this. Think out of the box. What is the traffic engineering in terms of civil engineering? Okay, I think other guys can also think on this.
So traffic engineering, I think that traffic engineering is the engineering which the network administrator done at his side as per the traffic pattern. Uh,
Okay.
as we know that there are multiple upstreams at the ISP level, and
Mm,
it is the responsibility of the NOC administrator to traverse the traffic uh, through different upstreams as per their demand. Like in ISP, we have multiple upstreams. Like some ISP belongs to Google, some belongs to UK or Malaysia. Then
mhm,
it is the responsibility of the network administrator to traverse their routes towards their destinations.
mm,
Uh, in this scenario, quality of service is also plays a vital role.
mhm,
With this, we can achieve maximum throughput with low packet
mm.
loss and jitter.
Okay, yes, that's a bit better answer. And but let
Right.
me define you. Yes.
When I think of traffic engineering, it can be done to optimize the performance of the network in order to cater the traffic of that network.
Yes, I think the word you used that you used the word. What's your name?
Puruj.
Uruj used the word that traffic engineering is used to optimize the performance of the entire network. So that's very close. But the other guy who spoke before Uruj is also right in more. He speak more technical details, and that traffic engineering is actually about network. It's not about users. Users are not aware of what engineering provider is doing. The main idea is that, for example, I think you all know about what is a routing protocol. Okay, can you give me an example of some interior or exterior routing protocols?
Sir, interior OSPF,
Okay,
exterior BGP.
BGP. Okay, so mostly within inside an autonomous system, the traffic is routed by protocols like OSPF and other kind of things. So mostly
EIGRP and
EIGRP. So do you think that the shortest path is the best path? If we allow routing protocols to work like this, and every routing protocol, every node is trying to select the shortest path in a certain topology, so do you think that the shortest path will be congested or
sir,
not?
it will be flooded. If
It will be.
it will be flooded if we are only using the shortest path first, then
If
it
you
will be flooded.
Yes, and I think that can you tell me what are the algorithm which are based on shortest path?
Sir, OSPF.
OSPF, okay. RIP is also, I think RIP is very rarely used now, but like still many algorithms, routing protocols, they use the shortest path scheme. So the main idea is that if all of the nodes in a network, which Uruj mentioned, that if they all are opting in a topology network, they're all opting for the shortest path. I can draw by showing a diagram, but like in this case, the shortest path can be heavily congested, and there may be other available links in the same network which can help you to connect end to end. But due to this routing policies, the routing protocols, these links are not used. Okay, so that's why even having the other available links, that and due to the factor that there might be more hops involved or other things as per metric of the routing protocol. These the other alternate links are not used, so that causes always the shortest path to be flooded, yes, as you mentioned. And obviously, when shortest path is flooded, then it will have more queuing delays, more packet loss, and end-to-end delay will be increased. So, and despite the fact that the overall network remains lightly loaded, but a few links are heavily loaded. So, traffic engineering is an exercise which is about which is done at. I will ask you the question again later, but it is exercise which is done to optimize the overall utilization of every link. Every link should be equally used. Ideally, every link should be equally used given end-to-end traffic load. So that's the main idea of traffic engineering. My next question will be, at what time scale traffic engineering should be done? Seconds, microseconds, minutes, hours, months, or years?
Sir, I think milliseconds.
I think then you are going into the first topic, performance analysis, because that's about less time scales. Net traffic engineering is something more than millisecond.
Sir, maybe
Uh,
according to the
Hmm?
of the flow, if that maybe take minutes or seconds or hours. If there is a large flow, maybe takes hours or days.
Mm, it should be. Let me check here, and I think this slide should give you an idea. I hope it's clear. Can you see the new slide?
Yes, sir.
Yes,
Yes, sir.
sir.
Okay. So
Yes, sir.
the same two tasks, the performance effects happen on a short time scale, and network engineering effects happen on long time scale. So that you should know. So and the boundary which Mark Crovella has proposed in his research papers and other articles, that around an hour is a boundary which distinguishes between short time scales and long time scales. Um, so you can see that microsecond, second, millisecond, and then hour, day, week, and then it goes from to months and years. So performance aspects are treated and evaluated at from nanoseconds to an hour, as per Mark Crowell experience. In case of my research, I disagree with Crowella because in my case, I propose that even 1 second is too much for time scales for performance parameters. If you see all of my research papers that which I have done analysis, that I even go till less than microsecond to nanosecond in my analysis and evaluate the performance at lower time scales. After like second and 10 second, the things change quite drastically. And I think that we should also consider the third dimension, which Crovella has not shown here. That although it's not very significant, but it should, you as an engineer should know. Which these things are ignored by. That's the difference between you and Crovella. Although Mac Crovella is a very good scientist, but he was not a practitioner. So, do you think that net performance effects like this and network engineering effects like, can you show what's the thing missing in this diagram? What is the third dimension which is missing in this diagram? Because this diagram is very easy. It's just saying that performance effects happen on short time scales from nanosecond to an hour, and network engineering effects happen on long time scales from an hour to months. Okay. So, and you know that what is network, you can just revise that. Performance analysis is about delay, throughput, packet loss, and network engineering is about capacity planning, traffic engineering, anomaly detection. We talk a lot about traffic engineering, and then this one. So I think that another factor which is missing here, and which can cause this the boundary, especially I'm more concerned about the boundary, which differentiates the time scales of performance and the time scales of network engineer. I think that this boundary is topology dependent. Okay, if you're analyzing an access network, obviously, then this boundary can change. If you're analyzing a backbone core network, then this boundary may change slightly. And if you're analyzing a kind of tier one network which is heavily loaded, then this boundary may again change. Okay, especially in the case of performance, because performance parameters differ when you talk of access network, backbone core networks, and tier one networks or IXPs kind of thing. So these are thing. But obviously, this does not affect our theory. But as an engineer, you should know about the differences. So this diagram is missing what kind of a network this is showing. Is it an access network or it's a backbone network? But still, it's our responsibility to map the theory proposed by Crowell or any author in a proper context. If we apply certain theory of performance, if we apply certain theory of network engineering, and we just read from certain paper and apply, it's not going to work. You should be, I think, our not network engineers will fully agree that without considering topological aspects, I mean access network even I can tell you that the boundary of this performance and network engineering, it differs even if the link matters, the link, if it's wireless link, if it's fiber optic link, or something different link. Okay, so but I hope that you get the idea that what are the performance time scales and what are the network engineering time scales. And then you can see that in the previous slides, there are two, I mentioned that there are two main uses for traffic modeling: performance analysis and network engineering management. Some principal differences that are of time scale and stationarity. I talked a lot about time scale here, I think, and you got the idea of time scales. Okay, and then the second point is about stationarity. So let me try to read the definition of stationarity. A stationary process has the property that the mean, variance, and autocorrelation structure do not change over time. Okay, so if the mean changes over time, obviously, then it means that this process uh, is not first order stationary. If the variance is changing over time, then it means that this process is not second order stationary. Okay, and autocorrelation is again a second order metric. Okay, if you remember that this is a square in the formula. Okay, same with the variance. The variance and autocorrelation are second order statistical metric. Okay, so if the mean, variance, and autocorrelation structure do not change over time, then it means that the process is stationary. If you see that I tried to elaborate more about this definition, although Mark Kurwala has written the definition is in a very easy manner, that a stationary process has the property that the mean, variance, and autocorrelation structure do not change over time. But if you have listened to me carefully, I tried to elaborate more. I tried to say, first, what do you mean by first order stationary? What do you mean by second order stationary process? If the mean is constant over time and the variance and autocorrelation is changing, then the process is still first order stationary, but you will call it as a first order stationary, not second order stationary. Okay, but if the mean is the same over time and the variance and autocorrelation structure do not change over time, then better you can call it as a second order stationary. I hope you got the difference between from this definition. First of all, you know what is a stationary process, and then you must know what is the difference between the first order stationary process, in which only means remain the same, and what is the difference between second order stationary process, in which variance and autocorrelation structure do not over time change over time. Okay, can anybody tell me about what is an autocorrelation? You can just read and tell me what do you mean by autocorrelation. First, okay, just tell me what is correlation. Anybody, what is correlation? I think this is very is you all have must have read about correlation in your undergrad.
Seven
So the
two.
mutual connection between two things
Yes,
or two
yes.
nodes.
If there is some connection between two independent variables, I mean they appear to be independent, but if you increase x, for example, there are two variables in variable x, variable y. Okay, variable x is time, variable y is cost. Okay, of some item. So if you increase time and then that cost is increasing day by day, then you can see certain correlation. Okay, if you increase time and then sometimes cost increase, sometimes cost decrease, sometimes cost again increase, so that does not show any correlation pattern, it does not show any correlation structure. But if there is some a specific trend, for example, if you keep increasing time and you observe a trend in other variable which shows dependency, increase in time lead to increase in cost of laptop, increase in cost of any book, any item, which happens in Pakistan always. They're always, the prices are hiking and they never decrease. So that's why this is there's a, so we can see that this is called as positive correlation between time and cost of certain item. Okay, so that shows the dependence of, if you change one variable and you notice the corresponding change in another variable, so that we call it correlation. It can be either positive, it can be either be negative. And in the same fashion, how will you define, so I tried to illustrate correlation, so how will you define autocorrelation? Okay, so how will you define autocorrelation?
So
You
the
can set the formula.
so the proportionality of same variables in different given set of observations.
Yes, yes. So if you try to observe, so in this case, there are not in case of autocorrelation, the word auto means that you are observing just one time series. Okay, you are just observing the cost structure or time data, whatever time series do you have. You are not trying to correlate it with another set of data. You are just observing the same time series and and trying to evaluate the dependence structure in time series, it just like previous value has impact on the next value or not, or a previous set of values has impact on uh, next set of values. If yesterday was very cold weather, so what should be the weather tomorrow? If it's again going to be very cold, it means that uh, it's autocorrelated in a positive fashion. Okay, and then if you see that if there is random pattern in weather first, just like we observed in Karachi a few days ago, that one day was very hot and other day was very cold, and then again there was a hot day and then again cold day. This, I think, situation these days are going like this. So we are not observing any specific autocorrelation structure in our case. So that's why, so if there is a certain, if you can notice that previous values are impacting next values, okay, then this means that there is presence of autocorrelation in your data. And autocorrelation is very useful in case of prediction, because if some data set like temperature time series or stock market time series or packet count data, session count data, flow count data, if it is autocorrelated, then obviously you must agree that it means that you will have the predictive power. Okay, so the autocorrelation helps you in predicting the next values which are going to occur, or even if that data is unobserved. So that autocorrelation, analysis of autocorrelation is very important. And if there is no autocorrelation in your data, then it means that the data is independent. And when the data is independent, there's no autocorrelation, then obviously you can never predict data. Okay, so presence of autocorrelation has certain advantages and it has also certain has also some advantages and also some disadvantages. The main advantage about the lack of autocorrelation is that the main disadvantage, sorry, that you cannot predict the future values. But the main advantage about the lack of autocorrelation is that there are a lot of statistical models which are available. Okay, because as the autocorrelation or dependence structure in your traffic data or whatever time series you're analyzing, if there is autocorrelation in there, then there are very few mathematical models which are going to help you. Then you have to use very alternate different models. A flat looking time series without trend, constant variance over time, a constant autocorrelation structure over time, and no periodic fluctuation. Okay, so that's called a seasonality. So I think you you got this thing, stationarity process. So I think that here you can see that the 1 hour stationarity connection, uh, and I think same thing. You can see that the difference. You can see that some uh, in which diagram, left or right, you can see the trend.
So in the left one, there
In
is a
the left
trend.
one, if in the left one you can see a trend, okay, and in the right one, there's a time series data which is also fluctuating, okay, but at least I am not able to see any trend. It just looks more random. Okay, so in the left one I can see, so what you can see, where is more correlation, in the left or right? Where is more correlation, in the left diagram or the right diagram? Right one.
So right.
In the right one, you see that I, I repeat the definition of autocorrelation. Autocorrelation means the previous set of values affect the next set of values, or in other words, a next value depends on previous values. It's somehow relevant to each other. Okay, so if you say that the right, I don't think in case of right, the right diagram, the traffic or the values, they are very much fluctuating, and you cannot, for example, if you can see the movement of my mouse is in the middle, so you are totally unsure that what will be the next value. You're totally unsure. Okay, uh, same goes with here. But if you come here, for example, like if you can see the movement of my mouse here, can you see my mouse movement?
Yes, sir.
So in this area where you can see the packet count or whatever variable is here, it's increasing with respect to time. Okay, so you can see a clear trend. Time is increasing, the value is increasing. So are the a value, a current value, depends upon previous values or not?
Yes, sir.
Yes, so it's depending. So that's called as correlation. And obviously, if you evaluate this correlation with the help of some formula, then obviously that's going to help you a lot. Okay, so that's why it's easy to see. It's easy to actually see correlation visibly, because here I've plotted the values here. So it's easy for you to visibly see from your eyes that when the data is correlated and when the data is not correlated. Same goes with the right diagram. In the right diagram, you can easily see that there is very less correlation or autocorrelation, because when I say I actually mean autocorrelation, because I'm not talking of two variables here. I'm just talking of one variable. You can see that the changing pattern in the both diagrams. In the right diagram, you can see the diagram, the traffic patterns are totally random. A value, any value anytime here is totally random, and it does not look to be dependent on previous values. You cannot ensure that what will be the next future here. Okay, the future prediction in the right diagram is very difficult. Okay, but in this diagram, you can see that this is a trend here increasing, and then there's also a trend. You can also see the second trend. Okay, which is decreasing, because as time is decreasing, the values are decreasing, decreases, and then it reaches again a certain threshold, and it start increasing. So you can see that it's the diurnal trend. Okay, uh, but this trend can be, our knock engineers talk too much about the busy hour and the less busy hour. This trend can usually be ignored up to time scales for about an hour, especially in the busy hour. So if you change the time scale of analysis, okay, if you change the time scale of analysis, then you might lose the observation which you are seeing this. Okay, I think you got my point, because this is very important point. In this the left part, the time scale has been chosen in such a way that you are able to see the correlation. Okay, you can see the dependence structure inside the values. In the right part, the right diagram, the correlation, the time scale has been chosen is that you cannot see any trend. Is it true? Can you see any trend in the right diagram, right
No,
box?
sir.
No, sir.
But my question is that is it by looking, just looking from your eyes, just looking from your eyes? Okay, can you show? Can you just conclude in a bulletproof fashion? Can you conclude that in the right box there is no correlation? There's no dependence.
No,
I
sir. We
agree.
have to. Sir, can we expand it and see further into the
Yes.
time scale?
So it means that a change of time scale uncover
Yes, sir.
can
Yes.
uncover if there is any hidden correlation. That's very important. Okay, so if you can with confidence, so I think the thing which I'm trying to teach you, you will get very soon. I think that defining the stationarity of a process, that okay, this process is stationary, is you cannot just say by plotting it. Okay, you have to plot that process or that values at different time scales. Okay, and then you need to conclude. Okay, looking at the traffic pattern, looking at the traffic variations at just single time scale, whether it millisecond, whether it's second, whether it's hour, whether it is even year. Okay, you might have seen traffic pattern in various reports of yearly traffic of Pakistan, yearly traffic of some country. Okay, so that's never going to help you. If you have to do traffic modeling, and then the very first task, you need to make sure that you are going to develop a traffic model. So the task you are going to do requires what kind of approach? Is there dependence in the structure? Is there any autocorrelation? Then you have to use a different route. Okay, and if there is no dependence in your data, if your data or internet traffic is completely independent, then you have to choose a different route to go there, because there are two different, totally different approaches. If there's correlation in the data, then obviously that you have to see, for example, in the right part, obviously we all agree that nobody of us can see that there's any trend in the right box. The values are totally random, and if I conclude that the traffic here is smooth, or traffic here is stationary. Okay, so the mean value, the one thing which I'm sure that at this time scale in the second box, if I give you a mean value, so can you say that the mean value is representative of or reflective, or it is a good idea? Yes or no? I repeat my question. In the right box, if I evaluate a mean value, okay, then or variance, can you say that it represents the process well? Yes or no?
Yes, sir.
Yes, it's true. It's yes. And if I go towards left part, and I just take all the values and compute single mean value. So is that single mean value in the left box, is it going to justify, or is it going to represent the data?
No, sir.
Why?
Sir, because there is a change in trend.
Because there's a change trend, and obviously then if you want to have especially in this left part, if you want to declare a mean value, you can say, oh, in the busy period, as you can see that because it's a diagonal graph, in the busy period mean is totally different, and in the less busy period the mean is different. Okay, so you actually have two different mean values which are justifiable. Even then it's not just to say two mean values, because the left part is totally not stationary. Okay, the mean is changing over time, the variance is changing over time. But in the right part, at the particular time scale which I have illustrated with the graph is showing, in the right part, the mean value is okay. You can compute mean value and it's not deviating too much from, and the variance is also okay. Okay, but again, remember one more, remember one point. I think this is clear how to analyze stationarity visibly, but remember one thing, which I'm trying to emphasize, is that just seeing the graph by your naked eyes is not sufficient, because at the moment right part looks stationary, the left part looks non-stationary. Okay, but the thing is that we cannot just declare by looking at the figures. We have to analyze. For example, the right part, it looks stationary or non-stationary. The right box is stationary or non-stationary.
Sir, by seeing by naked eye, it's stationary.
It's stationary. But if I change the time scale to hour
So
or
that
other
would
time scale,
change.
it if it still remain the same, then you can with confidence say, oh, that's stationary. But if you change the time scale, and maybe it's true that if you change the time scale, the the behavior in the right box, the right plot, can become the same in the left plot. That's always possible. And when you do data analysis, when I will teach you R Studio, I can show you the case that. And let me tell you that this is just the case of the same. These two are the same traffic, but it just looking at the different time scales, we can see that, oh, this one looks stationary and the left one looks non-stationary. So I hope that you guys, you all got my point at what is stationary traffic and what is non-stationary traffic, and how the time scale variation impact your analysis. Any question in this regard? Okay, I hope it's clear. So if you have any question, then just ask me. Okay. Uh, mm, mm. Okay, so we have some. We will skip some of the queuing part here. We will skip some of the queuing part here, but we will see other relevant points here. So, characterizing a stochastic process, an approach for characterizing stochastic process. For a stochastic process, which can be a random process, okay, the values, there can be potentially infinite set of properties to capture, and I think that you all have got an idea of what is autocorrelation. I mean, the dependence of a time series with itself. Okay, so if the previous values in the data affect next values, the data is autocorrelated. If the previous values in your data does not impact the next values, the values are completely independent, then there is less autocorrelation or zero autocorrelation in case of data. So that helps. Okay, so there are actually two approaches using margin distribution and and marginals and autocorrelation. I think you all might have studied this definition in your undergrad. Here, I'm just going to repeat and just an overview. Characterizing a process in terms of these two properties gives you a good approximation understanding of the process without involving a lot of work or requiring complicated models and or requiring estimation of too many parameters. Okay, so what is a marginal? Okay, so given a stochastic process x, okay, so x can be your packet count data, it can be your session count data, it can be your daily trends in stock market, whatever values of x, it can be your and we are interested in the distribution of any xi. Okay, so what that is, the probability that xi has some given value. So a small x is the given value and xi is your point of interest. So you want to make sure that this stochastic variable, which is capital xi, okay, because the capital X is equals to capital xi. So you should understand difference between capital X and the difference between small x. In all literature about probability, I think you all know about this, that the capital values are used as a random variables, and the small values are used as a fixed values. Okay, so just like in case of your the diagram on the right side, okay, you can see capital Y. Okay, the values are changing: 29.2, 99.4, 299.6, 299.8, 300, and 300.2. So these are the instance of that variable Y. Okay, and that can be small y, and then you can see counts on the left part. Okay, so and we assume that x is stationary. It does not matter which xi we pick. Okay, so we estimate by using just we plot a histogram. So what this histogram is showing, it's showing that uh, in your data, uh, what is the occurrence level or the probability of some values. So you can see that the chances of occurring 300.2 is very less because the counts are very low. Okay, and the chances of occurring value 29 299.8 or 299.9, these are very high. Okay, so this histogram is trend is just a summarized count of your data, which is telling you the marginal distribution of your data. Although it is I say that the histogram is not a complete picture of your data, but it gives you a very good idea. I think that, and I know that many of the knock operation guys and other see one big peak. Okay, and the structure shows that it looks like a bell curve, so it has a certain variance another kind of software. Okay, and what is the difference between the histogram and CDF, cumulative distribution function? The probability of your random variable, the density function. The histogram is often used as a poor estimate of the PDF, the density function, whereas because density function shows where your probability mass lies. I think if you remember correctly, in the last class, I told you about some of the details about the heavy tail distribution and the light tail distribution. I will talk more about them later. So the CDF, the cumulative distribution function, is defined as fx is equals to probability that the random variable is less. Okay, so this gives you a better good estimate of the properties in your data than the histogram, because the histogram may miss some of the values. The counts are not sufficient. Okay, so you should not just plot the variable and their counts. Okay, so convert on the right side. For example, what is the probability that the variable x is less than 4? Can you see from this diagram what is the probability Yes, please. Yes.
Sir,
In this diagram, I
sir,
hope this
your
slide is.
video is getting stuck again
Sorry,
and again. So your video is getting stuck again and again.
can you see the slide here?
Yes, sir. It's network traffic. Yeah, histogram and CDFs.
Yes. So my question is that what is the probability that in this diagram the counts are on x-axis and the probability on the y-axis? What is the probability that your traffic is less than 4? You can see that after two, if you can see that at this point, the CDF reaches 1, because the maximum value the CDF can reach is 1. Okay, so it means that uh, any value which is less than 2.5, in because all of the values in your data is less than 2.5. So if you talk of 4, 5, or 6, or any other value, then less than 1, less than 4, anyway. So in this region the things are changing. And similarly, what is the probability that the value is less than -3? You can see that the answer is 0, because no value, no probability mass lies before -3. So that gives you a good indication of the probability values, that how much likely a certain value is in your data set. I would advise that you capture your internet traffic from any Wireshark or anything, and just make the CDF and histogram. You will learn a lot. Okay. And modeling the marginals, for just this is just a same histogram which you have used. You can see that the values on x-axis ranges from -3, -2, -1, 0, 1, 2, 3. Okay. And then there's I tried to fit a bell curve on the data around 0. Okay. So that's why. So you should saying, okay, Poisson tail decay is very slow. Uh, Poisson tail decay is about different slowing varying pattern. Pareto is very slow tail decay. So there are different kind of distributions which can fit your data. Okay. Um, there are different. You can see in the slide that statistical method exists for asking whether the data set is well described by a particular distribution and estimating the relevant parameters. These are the things which we will study quite well later on, that if a data set is given, because we will be working on data set in later classes of internet traffic, packets, flows, and session. And the very first question will be that what kind of distribution which we should use to model this kind of data set. Okay. And then so there are methods which you tell it. And I think that I told you in the previous class there are various kind of fitness tests, like Anderson-Darling test and Kolmogorov's test. Okay, don't worry about the name. The names are quite difficult, but the things are very easy. So it's just about the matching mean and values. So it's another parameter. For example, let me ask you one thing. If there are two different data sets, data set 1 and data set 2, if the mean, can you say with confidence that these are the two, these are coming from the same data or same stochastic process? I repeat my question. If the data set 1 and the mean is mu1, if the data set 2 and the mean is mu2, so if the mu1 is equals to mu2, data are generated by the same stochastic process.
Yes.
So it means that so you can see that having an equal mean is an indicator of the equality of the stochastic process. Any other comment, any other remark? If the two data sets which are different and the values, the mean value is the same, if the mean value is same, then what about this? I think uh, let me use my tool here, and I should uh, okay. So can you see the slide, my the board here, the whiteboard?
Yes, sir.
Yes, sir.
So you can see that just like there, I'm sorry, this is okay. So these are the values here, and this is a data set. So this is the, sorry, so you can see that if we plotted the data like this, okay, so the mean value is something this, okay, and this is called as this spread is called as variance. Okay, this is the variance of data set. The more uh, the width of the this bell curve, your data set have a more variance. Okay, but is it possible that around the same mean the data behaves like this? Is it possible? Okay, so this is data 1 or this is data 2. Okay, so what is the common thing in about data 1, data 2? Both have same mean. We can have another data set, okay, and who's like this, that like this, sorry, it's the mean value, so it should be like, sorry, not, so it's like this. So you see that here the so this is mu1, mu2, and mu3. This is sigma 1, sigma 2, and sigma 3. So in this diagram you can see that mu1 is equals to mu2 is equals to mu3. So the mean values in all three data sets are this is your data 3. So the mean values are same, but you can see that the variance, the sigma 1, the sigma 2 is quite low, and the sigma 3 is quite high. Okay, so you can see that that variance 3 of standard deviation 3 is greater than 1, greater than the lowest one looks like 2. So, okay, so this is your standard deviation or variance. I think you just, if you just square standard deviation, you get the variance. So I technically there is no difference between standard deviation or variance. So now, can you, having said this, can you conclude that if two different data set has the same value of mean, does it mean that the data is same?
No, sir.
Okay,
No,
so I hope
sir.
it's because it depends upon the
Their
other metrics. If
variance.
the variance is high, then that spread will be high. Okay, okay. So um, the less the variance, the more the values are considered around mean. The more the variance, the more the values will be deviate from mean. So that's why. So you should understand the interplay of mean and variance. So just saying that the mean of the data is same, the data sets are is same, is not okay, because obviously you can. But the one thing is that uh, you should, what you will be very it, the thing which I want to illustrate you is that you all agreed that data 1, data 2, and data 3 has same mean. Okay, you all agreed, yes or no?
Yes,
Yes,
sir.
sir. Yes,
Yes,
sir.
sir. But you all agreed that they have different variance. Okay, they have different
Yes.
variance. So the stochastic process is different. Is it true or not? You all agreed that both three data sets are different, despite the fact that both three data sets has same value of mean. Mu1, mu2, mu3 are same. They are all equal. Okay, but their variance is different. So it does it mean that the underlying stochastic process is different or same?
So different because of variance.
Uh, because of variance.
Variance.
Yes, because variance is changing. So this means the values in the actual data will be quite different. Okay,
Yes.
although all of the three data sets have the same value of mean, but that's the point which I wanted to say, that uh, mm, uh, uh, that underlying. Okay, I will try to have more of your comments. Can anybody tell any other comments that both three data sets are different because the mean is same but the variance is different? So obviously the values will be different, and they appear to be coming from a different stochastic process. I mean, when I say stochastic process, obviously a process generates data, an arrival process or departure process. So we have to model this kind of process data, because a stochastic process is the driver, it generates data. So this data 1 can be generated by a stochastic process 1. This data 2 can be generated by stochastic process 2. This data set can be generated by stochastic process 3. My question is about that SP1, SP2, and SP3. Are these stochastic processes which generated data 1, data 2, and stochastic process data 3, data 3? Are these stochastic processes, this, and this, are same or different?
Different.
Any other comment?
Sir, the process will be same, but the given data sample will be different for.
So, any other comment? Muna, what you say? And
It's
Abdullah?
not, it's not
Yes.
clear. It's
So, what do you suggest, Muna? That because these three data sets have same mean but different variance. Okay. So obviously the data will be different. But do you agree that the stochastic process of data 1, data 2, data 3, all of three are the same or different? Hmm?
different.
Different. Why?
Are different.
But you know, I think if you see the what I want to illustrate you that the if the if due to the parameters data changes, then you must not call it as a the underlying stochastic process or data model is different. In this case, I would say that data 1, data 2, and data 3 are generated by the same stochastic process. The SP1, SP2, and SP3, they are the same, because you can see the distribution pattern of the data is same, although sigma 1, the deviation here is different, the deviation here is different, and deviation here is the highest. Data 3 has the highest data set deviation because the values differ too much from mean value. But you see that the if the changing if you change the parameter, certain parameter, and the data set values differ, and then it does not mean that you are changing the stochastic process. If the what I would my main comment before having a break is that if the distribution of the underlying data is same despite change in the moments, despite change in the mean values, despite change in the variance and other parameters, if the distribution of the data is same or the structure is same, then it means that the stochastic process is same. For example, in case of the diagram shown here, the stochastic process 1, stochastic process 2, stochastic process 3, these are all belong to which we call as a normal distribution, normal or Gaussian. And Gaussian process is parameterized by two parameters, mean value and sigma. So you can see that if the Gaussian process, you can use MATLAB or R, and then you can generate data. So you have to change mean value and the standard deviation. So you can have different values, but obviously the structure or the curvature or the density function of these values will remain the same structure. So that means the stochastic process is the same. So that's why I hope you guys you all got the difference, that the beauty of the data, how to evaluate the beauty inside the data, how to evaluate the hidden things in your data. That just saying that mean, so just saying that mean is equal, so the data set will be equal. You cannot just say that if the mean is equal, so that all the data are same. Okay. We should comment on the stochastic process which generates data. We should investigate more about the generating process. That will give you more insight. Okay, so you all agree that the mean in all three data sets shown here is same, but you all disagree that the values will be different. It was right, you are right that because when you see the actual values of this case, the actual values will be very different. The actual values here will be very different, and the actual values here, if you see the data set value, the time series will be very different in this case. True or wrong? Obviously you all will agree that actual values in this case will be different here. But when you compute the mean value, it's same. When you compute the variance, it is different. But the thing is that the distribution is same. Okay, they all look like a bell curve. Agreed or not?
Agree, sir.
Agreed. So it means that the underlying stochastic process is same. And let me tell you one more thing, that having the same logic, you having the same mu here, the same mu here, sorry, the same mu here, you can have another like this. Okay, this is another data set which has mu4. Okay, so it has also the same mean. Okay, and the variance here, the variance structure here, the division here, obviously it can be 5. So do you think that matching of mu4 and sigma 5 will cause this one to be equivalent to this one? This is stochastic process 4. You can see the distribution of this process is completely different. So this is so the final conclusion is that sp1, sp2, and sp3, these are all same stochastic process, but this one is a different stochastic process. Even though the mean value can match, the mu4 can match, the mu1 is equals to mu2 is equals to mu3 is equals to mu4. Okay, these can match, and the variance can also match, but the distribution of the data, it's different from the from or what we call it the two tail. Here in this curve, this one is a single tailed curve. Okay, which we have just single tail here, and then this is the tail decay here. Okay, so the distribution of the data is different here. So I hope that the main idea is that the conclusion is that we should not be hasty in defining the stochastic process. We should not just compare mean values. We just not compare variance. We should see the distribution. If the distribution of two different data sets, if the distribution of the three different data sets, or the distribution of 100 different data sets is the same, then it means that it is coming from the same what?
Same stochastic process. Have the same stochastic process.
Had the same stochastic process. I repeat, if the data set 1, 2, 3, 400 and 100, they are all if the distribution of this all data sets, the density function of this data sets is same, then it means that the stochastic process behind them is same, and the only things is the change of mean value or change of the variance, which so these are called as so I think that the confusing parameter, it should be clear now, that you should understand what is a stochastic process, what is a stochastic process, and what is parameters of stochastic process. Okay, so I hope it's clear. You should know two things. Number one thing, what is stochastic process and what is the parameters of the stochastic process. Okay, a stochastic process can be same, and it can, and if you change the parameters, the values will be completely different. The data set will look like completely different. Okay, but the stochastic process will be the exactly the same. So the change, so the main conclusion is that if you change the parameters of stochastic process, the underlying data set will still follow the stochastic process. The distribution, the density function, the behavior, the data outlook, when you plot them, they will look like the same. Okay, so I hope you got an idea of what is stochastic process. But if there are two different data sets, their mean variance, there can, for example, I can say that there are two different data set, data 1, data 2. In data 1, and in both data, when we compare them, so mean value of them are same, the variance of one is same. Okay, and the other metrics, what are the other metrics? I think you all know. Skewness 1 is equals to skewness 2. So does it mean that they're all coming from the same stochastic process? If I just give you this thing, forget about the what we have seen before. If I tell you just one thing, that there are two data set 1, data set 2, both have same mean values, both have same variance, they both have same skewness. So does it mean that they are coming from the same stochastic process?
Yes, sir.
Yes, sir.
Yes, sir.
Uh,
If
I,
if they have the same
I think
distribution.
Yes, so if they have the same, you can only say if they have the same distribution, only then you can say that these are coming from the same stochastic process, and the stochastic process is the same. But if but just looking at the thing which I have shown here, just looking at this, it is, you can never confirm that data set 1 and data set 2 is coming from the same stochastic process. If you just compare mean values, variance, skewness, unless and until you actually compare the density function, their distribution, only then if the distribution looks like same, then it means that the stochastic process of data 1 and data 2 is same. And then otherwise the distribution of data 1 can be, I repeat with a strong significance, I should repeat with a loud voice, even having the same mean, even having the same variance, even having the same skewness, data set 1 and data set 2 can come from a completely different distributions, completely different stochastic process. And I know that you guys must understand that this is very true. The distribution can take any form. There are infinite set of possibilities which a data distribution can take. And you might be confused because these are confusing values, that oh, mean is same, variance same, skewness same, and other higher moments can also be same, and you might lead to confusion. Oh, this means that, oh, that they are coming from the same stochastic process, but that might lead you to a disaster, that might lead to you a wrong conclusion. Unless and until you see the distribution function, you draw the density function and compare them, you can never be sure that they are coming from the same stochastic process. So I hope that in this part you got my point clear, that what's the stochastic process and what are its parameter. The main conclusion which I want you all to understand is that what is a stochastic process and how its parameter affect the data variation, and what is the differences, how will you know the differences in stochastic process. I hope it is clear, and before we take a break, I'm open for any question. I hope it's clear to you.
Sir, could you please told us about the skewness?
Skewness is the third moment. Mean is the first moment. Variance is the second moment, and skewness is the third moment. You can see the formula in any statistical book. It shows about the other parameters higher moment than variance. You can see the formula in your book.
In the current
I think
diagram, is it possible to view the
you can.
skewness?
There's also a parameter called as kurtosis. This is fourth order matrix. Sorry, kurtosis. Graphically, it's easy to illustrate mean and variance, and you can also see the skewness graphically. Okay, but kurtosis is different to illustrate that how much skewed is the distribution is on the right side. For example, I can define skewness is that for example, this diagram is symmetric. Okay, this diagram is like it's rightly. This one is left skewed. Okay, and this one is right skewed. This is left skewed. This is symmetric. So this is another, I think, it's just like the skewness, just the word means skewness. Okay, I hope you got an idea of skewness. Okay.
Yes. Thank you.
But the thing is that do not believe in what I show graphically. You should know the formula of skewness. You should know the formula of skewness. You should know the formula for mean value. You should know the formula for variance. You should know the formula for skewness. You should know the formula for kurtosis, because we will use them later on in the numericals. But it's good that you ask the question. So I hope that the main conclusion is that having the moments mean, variance, or skewness, if these values of coming from different data set is same, that does not mean that underlying stochastic process is similar, unless and until you compare the density function or the data distribution. Only then you can say, oh, these are coming from the same stochastic process, and the difference is due to the fact that only the parameters are different. So that's the main confusion which people here do not understand. So that if you know the stochastic process, and because that's the beauty of the stochastic process, that changing parameters of the stochastic process will give you a great variety of data. That is the main beauty. It does not mean that if you change the parameters and the values change, oh, it is a different stochastic process, it's a different thing, totally different thing. It never means like this. The parameters of the stochastic process, if you understand them correctly, then you get the real beauty in your hand, because then you get you can control your data, you can model your data if you understand the underlying governing parameters. If you do not understand your data, obviously then you cannot control or model your data. You cannot say that it's coming from any stochastic process. So there are two things which I want to repeat again. You must have an understanding of stochastic process, and you must know that how the parameters of the stochastic process, the mean values, the variance, how they impact the same stochastic process. So the change of parameter does not mean that the stochastic process has changed, because change of parameter will, if you change the parameters, the mean value and the variance, obviously the stochastic process will generate different values and totally different data sets. But that does not mean that a totally different data set mean that the stochastic process behind them has become different. Okay, so that how if the distribution, if the density function of two different data sets is different, and even if their means and variance are same, then it means that these are coming from two different stochastic processes. I hope my discussion is quite clear, and I think you all might have be tired by my speaking again and again, so we should take a break. Okay,
Okay, sir.
Okay, sir.
so we can take a break and then we can start again at 8 o'clock, and then we can have just a 20 minutes more class, and then we can finish. Okay, so please just click on the same link and you can, okay, you can. Okay, assalamu alaikum, welcome back. I hope my voice is clear.
Yes, sir. Walaikum salam.
Yes,
Clear.
sir. Walaikum assalam.
Yeah. So
Sir,
just
salam.
okay. Interesting things, because you might be get bored in my previous class. So I hope you can see the chat window, and I have shared the link here. Okay, I invite every one of you to just see this. I copy again the link, and I will be showing this link. I hope the link is working on your side. Okay.
Yes, sir. It's working.
Okay, so the main idea is just to show you that how it works, and you need to play around different distributions, how it looks. It will give you a good idea. I plan to, why I am showing like this. Just a moment. Let me do. Please allow me to do share screen. Press entire screen. So I hope you can see whatever I am showing on the screen. Is it visible?
Yes, sir.
Yes, sir. So you can see that what I have done, that I've opened the website here, and I'm trying to distribute. So let me just select from the distribution. I think in the bottom of the page, it's saying that using this tool to plot a statistical distribution online that you can download as a PDFs. The chart show the probability mass and the cumulative distribution function. You can also generate and plot random samples from the distribution. To get started, choose a distribution from the drop down list. Okay, and then so these are almost I can see beta, binomial, Cauchy, chi-square, Erlang, exponential, f, gamma, Laplace, Levy, logarithmic, logistic, log normal, negative binomial, normal, Pareto, Poisson's, Rayleigh's, student distribution, triangular, uniform, and Weibull distribution. So I think let's start from selecting the. I just select. I select what we were in the previous session. We were talking more about normal distribution or Gaussian, because Gaussian and the normal are the same thing. And if you click the details here, you can see the parameters are, what are the parameters?
So mean and
mean
And
mean
sigma.
value, okay, and the mean and the scale. And the scale here, actually they have given a different name. It's actually a standard deviation. A scale should be greater than 0. We cannot have a normal distribution with with uh, with I think you know that why it is greater than 0. Okay, because data should have the variance greater than 0. It cannot have a negative variance. uh, can mean can be negative? Can mean value be negative? Yes.
no.
I mean, if there's a negative data, or I mean, mean value can be negative. What's the average value of temperature in Iskardu now?
Sir, it's
What's the mean
negative.
value? It will be negative. The average value and mean value can be negative. There's no chance. But the variance cannot be negative. So that's why, because variance controls the width of the spread of your data. It cannot be like something like negative variance or negative scale parameter or negative standard deviation. It must be greater than 0. That's why it says that the normal distribution, the mean value, the mu, it belongs to, that symbol means belongs to R. R means, R
Real
means
number.
real number, and real number is any number. Real number is any number. It can be floating point, it can be minus, it can be plus, it can be, so mean can have any range. The scale or the standard deviation, it's sigma greater than 0. Why 0? Because you cannot have the data with standard deviation or variance which can be negative. There's no concept of negative deviation. It should, deviation is always positive. Okay. For example, just like in previous session, you know that the width of the bell curve, that was the scale parameter or the standard deviation. It cannot be negative. Okay. If the all values in the data are same, if the all values in the data are same, the mean value will be the same as any value, and the deviation will be, if all the values in the data are same, the deviation will be, the mean value will be the same. For example, you have 4 4 4 4 4 4, all 4 values. What will be, what will the mean?
Sir, the will be 0.
One mean will be 4, and the sigma will be equals to 0, because there's no deviation. So obviously in case of parameter, the distributions, we have the mean value and the scale parameter. So so we have support by x value, we have the density function and the CDF. Okay, so mean, this shows is skewness, and the excess curvature is 0 in this case. So these are just the details are showing just the parameters of this. We will understand more about this PDF density function and CDF later on. So I just tell you one thing. Let me do one thing. Let's do, the mean value is 5, and the sigma, you can see sigma is let's say sigma is 1. Okay, and just we need to, so you can see that you can see that it's plotted now. Mean value is 5 and sigma is 1. Okay, and then we can change sigma to 10. You can see change, we can sigma to 20. You can, so keeping the mean value same, you are changing the standard deviation or indirectly the variance, because sigma square is variance. Okay, so if you do like 50, you can see this. Similarly, if you do 100, you can see, so if you do 1000, so you can see that if the mean, so what is the conclusion? That if you mean value is 5 and the variance is 1000, so density function looks like a straight line. It's no longer, like a bell curve. So you see that the difference in case of mean value and sigma is affecting the data outlook. Okay, so what about if sigma is just 1? Okay, so let's do this 10. And if you can see the x value, what is x, your normal value? For example, if I say, okay, 5. Okay, so you can see I have written the 5 in the box. You can see that it's showing in the density in the left plot, it's showing the value 5. Okay, you can see that the point is just in the middle. Why?
Because we have taken the mean
because the plot shows the distribution of normal distribution with mean value 5 and standard deviation 10. And you can see that for x value, the actual value, I plotted to it just in the middle of the curve, the top point, the peak, or which we call as summit, because it's just a mean value. So what if you supply the mean value and the variable the same, it will always match. Okay, so that's why. So if you take it as a if you take as a 15, you can see that the point has moved. Okay, if we take it as a 20, point is moved. If we take it as a 30, the point is moved. And if we take as a 100, you cannot see the point because it's not actually lying in the actual range of this. Okay, so you can see that entire and you see that if I add 100 or 200, the entire CDF is 1. You can see because all of the values are less than 200. It's very clear. So I think that the main thing which I want you to illustrate is that you should understand the dynamics of the probability density function and the CDF, PDF and CDF. You can see that you can plot both things. So I hope you can get an idea. And how come you plot the actual point? You can just trace out the actual point in terms of density function and in terms of the cumulative distribution function, because density function gives you the probability density function, the actual data it shows, and the CDF is about the data less than some value. Okay, so you have this is just on the right part, it is showing the probability x is less than equals to x. Sorry, there's too much kids making noise at my home, so I'm sorry for this. So I hope it's clear. You can play around this. And can you tell me about any other distribution? For example, let's about see the exponential, because it's so exponential distribution, you can see the details. It's just one parameter, lambda. Okay, in terms of internet traffic, it's called as rate parameter, the traffic rate, the the bits per second, the bytes per second, the packets per second, flows per second. And it has support, you can see the support on x belongs to 0 to infinity. And the density function is very simple, lambda exponential minus lambda x. This is density function. Okay, and CDF is 1 minus e to the power minus lambda x. So I will show you how come this values come, and it's very easy to determine mean value and variance from the density function. Okay, so mean of that exponential distribution is 1 by lambda, and the variance is 1 by lambda square, and this qness is 2, and the excess kurtosis is 6 value, so it's fixed. Okay, so usually in just plot as lambda 2, so you can see 2. Okay, if we plot, just tell me. And this on the left side, this is the rate parameter we set has 2, and the left plot shows the density function, and the right plot shows the cumulative distribution function, CDF. Okay, with the rate parameter lambda 2, because in exponential distribution it's parameterized by just only one parameter, whereas in the previous case, the normal distribution, it was parameterized by two parameters, mean value and the variance, or standard deviation. Okay, so can you tell me any other value so just see the graph. I want you to note something. So lambda 2, the density function looks like this. Okay, it's an exponential. You can, and please also observe the decay pattern of the tail, this part, right part. So if I put the value 0.5, okay, so this is like this. If I put the value 2, so the point goes like this. If I put the value 3, the point goes like this. So you can just see the probability that x less than equals to 3 is 0.99752. Okay, and the probability that x is equals to 3 is equals to 0.00496. And obviously that comes your formula, because the formula just needs the rate parameter. I hope this should not be surprising for you, because if you give, because e is known, we know that e is 2.176, lambda is rate parameter, and x is your value on the x-axis. Okay, so it's very clear. You can evaluate both things yourself as well. Okay, so if I change, so just let me remove this variable. So let me change the variable lambda to 5. Okay, or change to 50, okay, or change to 500. So what I'm changing rate parameter. So do you think that the graph is changing or not? I change lambda equals to 5,000. You can see the impact. Is the graph change or not?
Yes, sir. The values have been changed on
But
the
the
graph.
structure or the decay pattern of the graph, is it same or
No,
not?
it's same, sir.
It's same. Okay, so that shows that that's the summary or the confirmation of the previous points in the last session before break, that changing parameters obviously change the values. It impacts your data, but changing parameter does not impact what?
Distribution.
The distribution, the density function, or the data behavior. Okay, so you can see so the way the data is decaying uh, uh, remains same, whether the parameter is 5,000 coming back to 500, I come back to 50, and I come back to 5. Okay, you can see that it's all that decay value, it's the same decay. So that's why. So and so this is the exponential distribution. So you can see that it has a different curve than the normal one. Let me try to show you another interesting internet traffic, and which is called as Pareto. Pareto is a kind of heavy tail distribution in which that, if you remember correctly, in the previous class in last week, I talk of data with extreme values. Okay, so this is scale value and the shape value, and I think I forgot one point. Let me go back to exponential. Let me go back to exponential. I just write 2, and you can see this here. Just write 20, you can see like this. So I think I want you all to note that whatever the lambda is, the lambda is 20. Can you tell me from where the graph is starting? The left
20.
graph is starting 20. Okay, I change lambda to 2. From where the graph is starting?
2.
I change lambda to 2000. Graph is starting from
2000.
2000. Okay, so are you getting some idea? Okay,
Yes, sir. We are
why is this? Okay, if I say 5,000, graph starting from
5,000.
5,000. Okay, and the values on the x-axis are just the values, resulting values of the interval time, because exponential distribution is a continuous time. It is used for continuous time data, so that's why you are seeing that on the x-axis. This is about the continuous values. Okay, so this is so. So so this thing I wanted you to know this, like, okay, and coming back to the and you should also know the fact that when x equals to 5, the values were on the x-axis were 0. 0.2, 0. 0.4, 0. 0.5, 0. 0.6, 0.1, 1.2, and when I do x 500,000, you can see the values on the x-axis are very less. Okay, so can someone guess what is going on here? Okay, I show you again. The rate parameter of exponential distribution is what now? Is
5.
is 5. Can you read out the values on the x-axis? 0. 0.0, 0. 0.2, and
0.4, 0.5, 1,
yes.
1.2, 1.4, 1.5.
Okay, okay. I
Sir,
change to 50. I change to 50. So what's the impact on? Just see the impact on both sides. I want you to see the impact on the y-axis. Graph is starting from 50. Agreed. And what's the impact
Yes.
on the right? What's the impact on the x-axis? The values are reduced. Actual values are
Yes, sir.
actual value, because small x, because what's the y-axis? Probability that capital X, the random variable, is equals to small x. Small x is on the x-axis. Okay, because this value is 0. 0.02, 0. 0.04, 0. 0.06. These are values of small x, and the y-axis is the probability, is your rate parameter. Okay, sorry, it's your probability. It's your probability here. Okay, you have to normalize it. Okay, and it's 500. You can again see. So I think you can guess that why the values on the x-axis are decreasing, because when you increase the rate parameter.
The exponential decays in a shorter time.
Yes, because obviously when you I think this is very for your operations guys, very easy to understand, because when rate parameter increases, then the inter-arrival time
Decreases.
of packet.
Decreases.
Okay, if you increase, for example, in a certain bus stop, there are buses coming very soon, very quickly, so that the inter-arrival time between buses is obviously very small. And at a certain stop or station, the buses are coming after where the rate of bus coming is very small, very low, then obviously the inter-arrival time will be larger. Okay, so exponential distribution on the x-axis it's showing inter-arrival time. Okay, so I hope you got some ideas, interpretation of this distribution. You should play around with this. Okay, uh, let me show you another one. I have selected what? I've selected Pareto.
Pareto.
Okay, Pareto. Let's parameter k greater than 0 and the shape parameter alpha greater than 0. Okay, support is x is k to infinity. So can you tell me? You can see, just see here. Try to uncover what we'll see, what we will plot here. But I want you to understand clearly. All of us, I think, except me, you all are studying Pareto for the first time. Agreed or not?
Yes, sir.
Okay,
Sir.
Yes,
but
sir.
I want you to before we plot. Okay, I want you to understand something. Pareto distribution, it is parameterized by two things: scale and
Shape.
Shape.
shape. Scale is k and shape is alpha.
Alpha.
Okay, alpha greater than 0 and scale parameter is
Also
k
getting
also greater
greater
than
than
0.
0.
Okay. So support is showing, what is support? Support showing that x belongs to uh, it ranges from small k to infinity. So it means that in when the data will be Pareto distributed with scale parameter k and shape alpha, the minimum value on the data set
K.
will be k. Very good. Okay, because although it shows scale parameters k and shape is k, but the support of Pareto distribution is start from k to infinity. So that's your actual data. So let me right now tell me one value of k. You can say any value like 12. Okay, and alpha is greater than 0. Alpha is equals to 0.2. Okay, so you can see here the density function. So you can see that this is the density function, and it's 12. Okay, so in this data, the minimum value is it's starting from. Let me change 12 to 120. Let me change 12 to 1200. Okay. Let me change 12 to 5. So you can see that the minimum value is what in this graph on the left side. The minimum value is 10.
Is
Okay.
10.
Okay. If I change it to 30, the minimum value in the graph is
30.
30. Okay. Okay. If
Right.
this is a kind of this is a tool which is the tool is configured to show the minimum value on the x-axis. But if we plot from the 0, if we plot this graph from the 0, so it means that the graph will start from
0.
0, and from 0 to 30 it will be 0. Okay, I'm
Yes.
not sure whether I uh, let me can you see this whiteboard?
Yes, sir.
So it means that if we same graph, if your uh, k is equals to what was the value k 30. So if you start from 0, okay, then it means that from it will be like this is 30, and then it will be like this, and then it will behave like this. So there's a discontinuity. It is 0 on 0 0 is from 0 to 30. This is the value of k. The k is the minimum value. Before k, the entire PDF is the entire density function is before
0.
k in case of Pareto. In
0.
case of if your data follows Pareto distribution, if your data follows the stochastic process, which is Pareto stochastic process, then it means that before the minimum value of k, the stochastic process generates the value 0. It's always
0.
silent. It generates nothing. and start from after 30, whatever is the case. And then, but when you plot it, and then obviously, sorry, this will be, it's like a discontinuity graph like this. That then start from this. So I come back to this. I hope you can see the browser now.
Yes, sir.
I would have been much happier if these programmers in this is essay code should have used this discontinuity, because I am not able to show the discontinuity behavior in case of Pareto here. So that's why I tried to show you by my pen here. So coming back to the point here, let's take the minimum value as 10. K is your minimum value, and the now we try to change the shape parameter. Currently it is zero point 0.2. I am changing. What I request you to be very careful and see that what I'm doing, I'm keeping the minimum value 10k same. I'm not changing it. Okay, but I'm changing alpha. So I want you all to note down how this density function, the plot in the left side especially, because density function is more important to understand the behavior of your data. I'm changing the alpha. I'm doing it. It is zero point 0.2. So just see how the behavior of the plot on the left side behaves. I'm doing zero point 0.5. Okay. What is the difference between zero point 0.2 again? Zero point 0.2. Okay. And zero point 0.5. Let's do it again. Zero point 0.9. Let me do it 1. Let me do it 1.5. Let me do it 1.7. So can you see the impact of the, let me go back again to point 5. Let me show you more severe case, 0.3. Let me show you more severe case, 0.2. Another severe case, 0.1. More severe case, 0.001. It's going out of graph, but point. Let me see. So what you can see? Can you? I think you will better see when you do it yourself. So what you can conclude that changing alpha, the shape parameter, how does it affect your the graph and your data? Can you guess it? I think I invite every one of you to copy the link I shared in the chat window. Okay. Those of you who joined late, for them, I'm sharing them again. I'm sharing the link again. This is the link which I'm following. Okay. Try to click it, and you see the Pareto distribution, and then you so anybody who can conclude what is the impact of the change of shape parameter on the Pareto distribution stochastic process. I just want you to note visibly. I know actual details of Pareto. You are studying Pareto for the first time. I know that you are. I'm not asking you any technical thing, but I want you, because you are humans. You can see the graph. That's why I wanted to say that. See what I'm doing. I'm changing alpha, and I invited you all to see the left graph. How? See from your naked eyes how it's behaving. Let me try you again. Point one, then point two. Okay, just see the difference. Point one alpha and point two. What was the difference?
So the start point on y-axis is changing.
It's
Sir,
changing.
sir, if I increase the alpha, the line will be a straight line.
Yes, if you increase that way, observe why it becomes a straight line. I will tell you. Actually, it's not a straight line. It's just the problem of the scale. We are not able to see the scale, the data, the distribute, because you still see that what I'm plotting. I'm still plotting what Pareto distribution. The distribution is same. So if the lines become straight and the graph is not able to show you, the graph is not such scales. So it does not mean that it has become a straight line. You're just looking at one part. Okay, so that's why I'll always say that see the full PDF, and we need to draw it ourselves, because this particular tool is not showing us the for example, you are right, because Muna says that if you put alpha is equals to 1000, it becomes, or sorry, where is this? Pareto. So K was 5. and it was zero point 0.1. So you can see that if you do it's zero point 0.2. So just note down that the area under the curve on the right part, you can see the tail part. If you increase alpha, that the tail is tail decays faster. It's zero point 0.1. Can you see the difference between zero point 0.1 and zero point 0.2 when I change alpha?
Yes, sir.
Higher values on the right hand side have larger chances of occurrence because the right side, the tail part, so it has this part is more likely in case of zero point 0.1, and in case of see is the probability is decreasing. Okay, in case of 0.3, again you can see the probability of the extreme values is decreasing. So I think if you so let me ask you one thing. If am I right to say if you increase alpha, the chances of the large values or the extreme events becomes less, and alternatively if you decrease alpha like 0.2 of the extreme values in a data set, I mean the values on the very right side are more likely. Am I right to say like this?
Yes, sir.
Okay, so that's so I just want you to notice what is Pareto distribution, how it is made. That I will tell you. In fact, in one class x power alpha plus 1, how it came into being. I will make you derive all these formulas. This is not very something very difficult. These are all very natural and very easy things, nothing to worry about. I will tell you all of this, how this Pareto PDF is being made. But the underlying governing principle behind Pareto distribution is very interesting. Underlying principle behind that the Pareto distribution or the Pareto based stochastic process is very interesting. And I can tell you one thing, that the data or the basic theme or the basic idea or the basic philosophy behind the Pareto distribution is that the famous notion we all believe that the in this world belongs to how many people? 20% people. Is it true or wrong? 80% of the wealth in this world belongs to 20% of the people. I'm not sure
True.
how we call it in Yemen on Arabic. This kind of behavior that the rich the riches are in very few hands. There are few people in the world who are very rich, but their richness level is very high. Okay, so this kind of asymmetry is natural. So again, I repeat, the underlying principle behind Pareto distribution is that the 80% of the wealth in this world or the money in this world belongs to 20% of the people of this world. The rest 80% does not have so much wealth. I think it's true. True or not?
Yes, sir.
Yes, sir. True.
Yes, sir.
Yes, sir.
So,
True.
so that's why that's why. So this is about the if we talk technically. So this distribution is also called as extreme value distribution. What we call it EVT, extreme value theory. So Pareto distribution has been based for the extreme value theory, and the guys from the stock market and Financial Times series and earthquake engineering, they are quite fan of this distribution because they help to capture this kind of extreme value behavior. I think in case of because the main advantage of using Pareto distribution is that it is able to model extreme values. Otherwise, none of the distribution which I've studied till now. In case of normal, in case of exponential, the extreme value probability is almost near zero. But this distribution, the Pareto distribution, based on that low values of alpha, it the lowest the value of alpha, the better the Pareto distribution can model extreme values. Okay, so you can see that at this moment, this distribution is assigning, for example, if I say 70, it is giving you 70.02 probability. If I increase to 0.5, okay, so you can see the probability is P70 is 0.02. Let me increase to 0.9. It becomes 0.01 decreasing. Okay, so whatever you I said 1.5, so almost the 70 is almost the chances of 70 is almost
Almost zero.
almost zero. Okay, and but I so you increase alpha, then it means that you cannot model the extreme events. Let me come back. I do it zero point 0.5. You can see it is almost 70.02. Let me do it zero point 0.1. You can see 70 is it's increased. You can see the mass has been increased. Okay, it's almost 0.02. Let me do it point. It's gone too high. Okay, so that's why. So it's all about how you do this. But I would like that I would, so I hope you got this basic idea of this and this, and you can just change these values to, let me show in plotting or not. I have to plot it again. Any other distribution which we should try? Poisson is very common distribution. Poisson, and is used for modeling count data, in, like packet count data, like packets per second. It's not about interval time. So it's again it's very similar to the rate. The rate parameter is very similar to the used in exponential distribution. And let me give it 5. So you can see that in case of discrete distribution, it is giving you the probability mass function, because for discrete for the data which is discrete, you do not plot a density function, you plot a PMF, the mass function. I hope you might have studied this. So it's value 5. So you can see the behavior of mass function in case of Poisson distribution. If you change it to 50, it will behave like this. Okay, so this is the behavior of 5. If you change to 1, it behaves like this. Okay, change to 2, it behave like this. Change to 4, so you can see the shifting pattern of the density function. And to 6, you can see this. So it's changing to 30. It's like this. So one can say that if you increase lambda, you are trying to matching with Gaussian distribution. Is it true or not?
Yes, sir.
Yeah, so it's so sometimes distribution based on their parameters, it they convert to Gaussian distribution, and you can see that Poisson distribution tends to Gaussian distribution when the rate parameter is quite high. Okay, but and you can see that later on when we see the theorems regarding the applicability of Gaussian distribution, you can see that there are many cases in which the distributions converge to Gaussian distribution. For example, if you multiplex traffic, or if you see the like this value, if you increase the parameters, so sometimes distributions, not all, but some distribution converge to Gaussian distribution. But if I click on this chart, you can see the distribution. If our traffic follows various types of different, for example, on one link traffic follows Cauchy, on other link traffic follows Erlang, and other things. So if we multiplex such kind of traffic, then we have a theorem which is called as CLT, central limit theorem. It says that when the number of links in being multiplexed tends to infinity, and time factor also tends to infinity, that then traffic tends to Gaussian. So this is called as central limit theorem. Don't worry about this. I will teach you in this more formal way. So I hope that in this class you might have learned a lot about distribution. I would invite you all to see other distribution. Erlang distribution I have also used in my undergrad. So you can see. So you can, this is Erlang, and this is log normal distribution also. You can see, and 4. So it's a kind of, you can see the difference between normal and the log normal. It's kind of inverted of the normal. You can see that it's 1, and as you can see 2. You can see the behavior of this log normal distribution. You can see the behavior is similar to like kind of Pareto distribution. It also looks heavy-tailed, but the behavior is somewhat different because it always start from 0. It's not like Pareto, because you can see that the support is of the log normal is x0 to infinity. So I hope that this website will give you a good idea. I invite you all to, before coming to the next class next week, our fourth lecture, I would invite all of you to play with this tool, online tool, and then plot just with a special focus on exponential, uh, binomial, normal, Pareto, Poissons, uniform, and Weibull. You can see the Weibull. You can see the Weibull distribution. I have done a lot of work on Weibull, and you can see this is density function of Weibull. So you can see that how we change um, the the distribution tail. You can see the impact of the changing parameter of the on the distribution tail. So this tool will give you a good idea how the distribution function behaves, how various kind of, because these are all stochastic processes, and it will be very great if before coming to the next class you just explore this online tool, just plot the PDF density function, and also see the value of x, that what the value of x, how come this behaves, that how come if you change value x to 0.15. See, you can see that how it's showing your data probabilities and the point in the actual data. So I hope it is clear. So so we should stop class now. Thank you for your time. And we have a comment here: changing alpha will change the y-axis by increasing and decreasing order. Yes, I mean you need to observe these trends. Okay, so I hope it is clear. And now I am open to any other question. Okay, so I hope today's class you might have learned some interesting things.
Yes, sir. Yes, sir.
Yes, sir. Definitely.
So
Yes,
coming
sir.
back,
Thank you, sir.
so just and I think we cannot always depend on such kind of web-based tools. How many of you have installed this?
R Studio.
Yes,
Sir, I have installed
because
it.
yes, so
Sir,
that's
I
very
have
good.
installed it. Yes, sir, I have
So,
installed it.
okay, so
I installed it.
so assignment for you for the R Studio, because in future because it's not good to use professionally. It's not good to show which I did just now. I used the online tool and changed the parameters and showed you the variations in the density function. You should do it yourself. Okay, in R. Okay, so do the same thing in R. Okay, exponential Pareto. See how you generate the random variables of exponential. How you don't generate the random. For example, in case of R, you write the command R x. You can give the value of 12 and then 1000. So this is the command used to generate 1000 values of data which follows exponential distribution with mean value 12. So this is the similarly R voice, if you give 40 and then 40 and 1000. So this will generate 1000 variables, 1000 random variables coming from a stochastic process which follows Poisson distribution with mean value 40, with rate parameter 40. Same with goes with R variable. Same goes with have you need to get these variables running, sorry, these commands running in your machine. You will actually enjoy it. Then you can actually see the data and then plot them, and then plot the density function, plot the histogram, plot the mass problem in RStudio. Then you can see the from the studio GUI interface, you can see the a toolbox related to the statistics. That just play around the toolbox and you will learn a lot. Okay, if you do not know the commands here, the toolbox of the statistics will help you a lot. So I hope I recommend each and every one of you to use RStudio, because from the next class I will be using RStudio to demonstrate my task here. So I hope it's very clear. And before finishing the class, I must thank you all for listening to my lecture. I hope that I tried to elaborate main things. I would like to summarize what I have studied or taught you in this class. In the beginning of the slide, I tried to illustrate you the difference between performance analysis and the task of network engineering and management, and their time scales of relevance. And then I talked about how a stationary process looks like and how a non-stationary process looks like. And then I also illustrated that how the impact of the change of time scale affects the stationarity. Okay, then I Then I tried to show before the first session expired. I tried to show using my pen. I tried to show the impact of the change of parameters and on the data itself by showing what's the difference between different type of stochastic processes. So change of parameters does not mean that stochastic process behind the data has changed. If the underlying stochastic process or distribution of the data is same, then it means that the stochastic process of your data set or internet traffic or whatever traffic you are say looking at is same. Changing parameters is a different thing. Changing parameters does not impact that the stochastic process has changed. Okay, so and then after the break I tried to illustrate you different type of distributions and how they behave with respect to the change of parameters. So I hope that you got some of the points in during the class, and from the next class we will study more interesting topics and some of the numericals, and the course will become more and more interesting if you keep following my lectures and the tools which I am recommending. So I hope that it's okay, and any question you can ask, or we can. I have taken your attendance using the online tool, so don't worry about this. So if you have any question, then you can ask me, and you can leave the class. I will remain here in the class for any questions for 5 minutes or 10 minutes. Otherwise, any questions, I am ready to answer regarding today's lecture. Any question? Looks like in the previous class there were so many questions, and I kept talking till 9:30. It looks like today is no question. Muna, Abdullah, do you have any question?
No, sir. Thank you.
Okay, so you can leave the class, but still we have 32 students. Thank you, Mas. Thank you.
Thank you, sir.
Thank you.